The composition-dependent equilibrium constant can once again be expressed in terms of the pressure as well as the mole fractions of each of the components at equilibrium. To realize what will happen with an increase in the inert, realize that that will increase the total amount of moles in the mixture. Express each of the mole fractions in your equilibrium expression in terms of its number of moles divided by N total. After simplifying, we see the dependence on the composition-based part of the term with an increase in the total number of moles. Since the equilibrium constant is not a function of the number of moles but only a function of temperature, if this goes up, it means that the amount of methanol in my mixture at equilibrium must go down and the reaction will be inhibited. We know that the reactants are fed in stoichiometric ratios, and we have this unknown amount of carbon dioxide initially fed to the reactor. Using our stoichiometric table, we can now write the total number of moles at equilibrium in terms of two unknowns, epsilon, and the ratio of carbon dioxide to carbon monoxide. Writing the conversion of carbon monoxide in terms of epsilon and the initial number of moles in the reactor gives us our first equation, which proves that the conversion of carbon monoxide is equal to epsilon, which is equal to 0.6. Now we can write our mole fractions in terms of the only remaining unknown in our system, which is the ratio. Our second equation, of course, is from the equilibrium constant, from which we can solve the ratio R. The very huge equilibrium constant that we calculate at 423 Kelvin for the carbon deposition reaction shows that equilibrium favors the forward reaction. Using the mole fractions calculated in the B part of our problem, we can calculate the K, composition-based K value, at equilibrium in our reactor. Since this value is much smaller than the calculated equilibrium constant, the reaction wants to proceed in the forward direction in order to correct the balance, and therefore carbon will definitely deposit. However, since the rate of deposition is so slow, we assume that it will not affect the equilibrium composition in our system that we calculated just considering reaction 1.